Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to continue talking about the estimation of population parameters from limited data using random samples. We're going to introduce a metric called the standard error that allows us to evaluate how well an estimator approximates the parameter of interest for different number of data. Let's get to it. We're going to talk about the standard error. To begin with, let us remind ourselves of our setting of interest. We want to estimate population parameters, which are quantities that could be computed if we had access to the whole population, but cannot typically be computed in that way because it is too costly to go and measure every individual. For example, if we wanted to estimate the average weight of the rats in New York, we would have to go and catch every rat, which would be impossible. Instead, we obtain samples from we sample a random subset of the population and produce an estimate just from that subset. Here is a control scenario where we have 4,000 individuals. This is our population that we don't want to completely measure. Instead, we're going to pick a subset of the individuals, and our goal is to estimate the mean of the height of the individuals of this population. The height is equal to a certain number. This is important. We're in a frequentist setting where we model the parameter of interest as a certain deterministic constant that we aim to approximate. It is not random. But our measurements are random. We pick a random subset independently and uniformly at random from the population. In this particular instance, we are picking 400 samples from the whole population. Here you see the histogram of the whole population in white and the histogram of our samples in gray. And our hope is that the estimator computed just from the gray samples will approximate the the quantity that would have been computed with all of the samples using the white histogram. In this case, the quantity we're interested in is the population mean, which is the mean of the height in this population. And here our sample mean produces a very good estimate. It is important to emphasize that even though the parameter is deterministic, it's just a constant equal to this guy is not deterministic. Why? Because the measurements change. Like if we were to repeat the measurement process and take 400 other samples, we would get a different estimate. You can see that this histogram has changed because we have selected a different subset of 400 individuals from the population. If we repeat that, again, we get a different estimate. Here, we're going to see, I thought I was going to show you the histogram of all the sample means. We will see it in a moment. But before, let's remind ourselves how we model this measurement process, which is random. So these are the data from the whole population. Big N is the number of points in the whole population. What we get to see is n data points that are random. The way we model this is that each data point is selected uniformly at random from the population. There's the same probability of picking each individual, and they're independent. So that means that their distribution is independent and identically distributed, and the PMF of each of these measurements, of each of the random variables representing the measurements, is the same. It's equal to 1 over n for each of the possible values in the population. Okay? So hopefully that makes sense. So now, this is a plot that I thought I was going to show you a slide before. This is what we see when we look at 10,000 subsets of size 400. Before I showed you 4 examples. If we repeat again the measurement process 10,000 times and we look at the histogram of the corresponding sample means. So if you remember, the heights are kind of distributed all over here. In contrast, the sample means are tightly concentrated around the true population mean, which is 175.6. So this indicates that random sampling is working in this case because we get a very good estimate, very close to the population mean with high probability. But we have to reason probabilistically about this estimator, which is the sample mean. It's just the average of the subset that we pick. We cannot reason deterministically about it because every time that we perform the measurement, it changes. So because of that, we have to model our estimator, which is, again, the average of the 400 samples in our example, or however samples we take, as a random variable, which is the sum of the random variables corresponding to each of the measurements, and then we divide by the number of measurements. We already saw in the video on random sampling and the bias that for the sample mean, we're guaranteed to be centered at the population mean. If we look at the distribution of this sample mean, this is the empirical distribution from our experiments, we see that it is indeed centered at the population mean, which is great news. You know, it's nice that the distribution is centered at the population mean, but the question arises about whether that is enough to guarantee that we get a good estimate. Think about it for a moment. The answer is no, right? Because we could have seen a distribution centered at the population mean with a lot of variance. And in that case, with pretty high probability, we would get a very bad estimate of the mean height in the population. So we not only want the distribution to be centered at the right place, centered at the population mean, we would want the distribution of the estimator to have as narrow a spread as possible, to be as concentrated as possible around the parameter of interest. And this is precisely what the standard error measures. So we have n random measurements, and we're trying to estimate a deterministic parameter of interest, gamma. The standard error of an unbiased estimator that is centered, whose distribution is centered exactly on gamma, is the standard deviation of, it's its standard deviation. Okay, so the variance of the estimator, square root. Why do we call this a standard error? Well, the key observation here is that the estimator is unbiased. What does that imply? It implies that the mean of the estimator is exactly equal to gamma. So when you look at the variance of the estimator, by definition, it's the expected value of the estimator minus its mean squared. What is that? If the mean is equal to gamma, that's just the mean squared error. Okay, so for unbiased estimators, this standard error is nothing else than the square root of the mean squared error between our estimator and the parameter that we want to approximate. So it makes sense that we want to have it as small as possible. So now let's derive the standard error of the sample mean. We have already seen that the sample mean is unbiased. The square of the standard error is the variance of the sample mean. By definition, the sample mean is the average of these random variables that represent our random samples. Now, the 1 over n can come out squared because the variance at the end of the day is the expected value of the random variable minus its mean squared. So then, by linearity, we can take out this constant squared. And now we have the variance of a sum of random variables. Before, a couple of videos ago, when we were talking about correlations, we saw that when two random variables are uncorrelated, the variance of their sum is just equal to the sum of their variances. So we can directly apply that result here. Because independence implies uncorrelation, here we can split this sum into A1 plus the sum from k equals 2 to n of AK. Okay, so if we're looking at, I actually went a little bit quickly here. I'm looking at the sum of any n independent random variables. Why? Because by assumption our random samples are independent. Okay, so sorry that I went very quickly there. So what is the variance of the sum of independent random variables? Well, we can separate this sum into the first random variables and the sum of the rest. These are independent by the independence assumption. They're also uncorrelated because independence implies uncorrelation. So the variance of this sum is equal to the variance of the first random variable plus the variance of the sum of the rest. But then we can apply this again, separating the sum into the second random variable and the rest, and so on and so forth. So here, so hopefully you can see that this is just going to be the sum of the variances. Of course, I always have to have a typo, no matter how long I stare at my slides, I always need to have a typo. And if you find any others, please let me know in the comments. Hopefully there won't be, but they always creep in somehow. In any case, hopefully the logic is clear. The variance of a sum of independent random variables is equal to a sum of their variance because they're all uncorrelated, so we can apply this result that we had derived earlier. Why am I telling you this? Well, we had seen that the standard error squared is equal to 1 over n squared times the variance of the sum of our random samples, but our random samples are independent by assumption. We're assuming that we sample independently, and this is crucial in order to obtain, in order to guarantee that random sampling is actually going to work and give us a good estimate of the population parameter. And this is why, because under that assumption of independence, now we can write this as the sum of the variance of each individual measurement. What is the variance of each individual measurement? Well, just by definition, it's that measurement minus its mean squared. We take the expected value or the mean. What is the mean of each measurement? It's just the population mean, as we had shown earlier. So now if we write this in terms of the PMF of the measurements, which remember each measurement is equal to every individual in the population with probability 1 over big N, where big N is the number of individuals in the population, we obtain this formula where we will plug in 1 over N here. And what we obtain is basically the variance if we compute it over all the individuals in the population. This is called the population variance. It's just a parameter, it's a constant that you can compute if you look at all the individuals in the population, and that's the variance of each of the measurements. It's also a population parameter, by the way, which you might be interested in estimating. But now we see that it governs the standard error. The standard error is equal to the square of the population variance, how much variation we see in the whole population, divided by n. The standard error, therefore, is the population standard deviation obtained by taking the square root of the population variance divided by square root of n. Notice that there is no dependence in the number of individuals in the whole population. That's the first important thing to notice. The second crucial thing to notice, and this is a fundamental result in statistics, is that the standard error of the sample mean decreases with square root of n, n being the number of measurements. So this immediately tells us how the accuracy of our estimator is going to scale as we gather more measurements. There is no dependence, I already said this, there's no dependence on the number, which can be a little bit counterintuitive. If you think about it, it makes sense, but it doesn't matter. Like the total number of individuals in the population does not matter for the standard error of the sample mean. Okay, so let's go back to our example. Here we have just 20 measurements out of a total of 4,000, but again, this doesn't matter for the standard error. Here, the standard deviation of the whole population, which would be obtained from this histogram of all the elements all the individuals in the population, is 6.85 centimeters. This is what we see when we take a histogram of 10,000 means. The estimator is centered at the population mean and has a certain standard deviation. And what our formula for the standard error tells us is that this standard deviation is going to be equal to the standard deviation of the population divided by square root of n. As we increase n, think about what is going to happen. Think about it for a moment. Well, what's going to happen is that the distribution is going to get squashed. It will remain centered at the population mean because we know that the estimator is unbiased. And now we also know that the standard error, is going to decrease with square root of n. So as we increase n, it becomes more and more concentrated around the population mean. When we have 1,000 measurements, it's already very concentrated around the population, as predicted by our result. This is another way of visualizing this. Here you see the number of measurements, and here there are sample means. Each of these points is a sample mean with this number of measurements. In this case, that would be like maybe 120 or something. As n increases, we see that the spread in the sample means decreases following this trend, which is 1 over square root of n, which is what we expected. Just to be clear, this line is the population standard deviation plus divided by square root. Sorry, it's the population mean plus the population standard deviation divided by square root of n, where n is the number of measurements. And the other one, this other line, is the population mean minus the population standard deviation divided by square root of n. And we can see that the distribution of this sample means that we obtain numerically exactly follow the formula that we expect. So now we're going to see how this affects an estimate of a population proportion. So we're going to look at this other example where we imagine that we're in the midst of the pandemic and we want to estimate the prevalence of COVID-19 in New York. And it turns out that the true prevalence is 5%, but we cannot afford to go and test every single New Yorker. We need to take a subset of New Yorkers and try to get an estimate from that. So just this is the same setting as before in the sense that the samples are random. So here we're seeing the proportion of positive to negative cases in the whole population. Realize that this is logarithmic. There's 8 million people, and we're only seeing a very tiny subset of them, okay, in particular 1,000. And we hope that this proportion is a good estimator for this proportion. Again, when we take different samples, the sample proportion is actually going to change. All right, so we have to analyze it probabilistically. If we look at 10,000 subsets, they're centered, like the distribution of the 10,000 sample proportions computed from this subset are centered at the population proportion, and they're quite concentrated. So things are looking good, but we want to analyze this more theoretically. So we saw in the previous video that we can have like a probabilistic analysis of this situation where we consider that the data, there's like one data point per individual, which is equal to 1 if they have COVID-19 or any other condition that we're interested in, and 0 otherwise. And then we can consider a random samples x1 to xn, where little n indicates the number of measurements. And those are IID random variables, which are basically equal to each of these guys with probability 1 over big N, where big N is the number of individuals in the population. We saw that in that case, what is the sample proportion? Well, you just sum how many of these guys are equal to 1. So you sum them, basically. And then you divide by the number of measurements. So this is actually just the sample mean of the random sample. So we can apply our previous result. The standard error is just going to be equal to, another typo here, the standard deviation, the population standard deviation divided by square root of n, okay? However, you might be saying, okay, sure, I understand what the standard deviation is for the height example. It's just the standard deviation of the whole population. I take each height, I subtract the population mean, I take the square, and then I average over my whole population. What is the standard, the population standard deviation in this case? Well, let's compute it. The variance, the population variance, which is the square of the population standard deviation, by definition is each data point minus its mean. We computed the mean in our video on random sampling and the bias. The mean is just equal to the population proportion. How many ones are there in the whole population divided by the total number of individuals. And now we can just expand this. When we expand the square, we get this formula where now we have to realize that the AIs are either 0 or 1. So this is exactly the number of ones in the population divided by n. So this is just the population proportion. This is again the population proportion, but multiplied by the population proportion. So here we have minus 2 times the population proportion squared. And here we're just adding a number n times and divided by n. So we have something that is equal to that number. So what we obtain is that the whole formula is equal to the population proportion minus the square of the population proportion. This should not be a surprise because essentially this is the variance of a Bernoulli distribution with this parameter. Okay, so we have essentially rederived that for the population. That's the population variance when we're dealing with proportions. So we can go back and plug that in. Unfortunately, I have this typo here, but the typo is not underneath. And what we see is that we get the product of the population proportion times 1 minus the population proportion divided by n, square root of that. So what can we realize? Well, this is just a number between 0 and 1, and we have this dependence where the standard error again decreases with square root of n. Let's take a look at some computational experiments, because it's easy to get lost when you're doing these derivations and these proofs that the standard error scales in some way. It's always good to take a step back and look at some numerical simulations that illustrate exactly what we're proving. So here, let's imagine that we have a population of 8 million people, like in New York City, and there is a prevalence of COVID-19 of 0.05. This is what happens if we measure 100 people at random over and over again. Okay, we repeat this 10,000 times, and we look at the distribution of our estimator. So the estimator is actually centered at 0.05, but there is quite a bit of spread because we have very few measurements. As we gather more and more measurements, the spread becomes less and less. We obtain an estimator that is centered at the population proportion, which is what we expect because it's unbiased, and we see that the standard error, the standard deviation of these sample proportions converges to 0 with a rate that is exactly what we expect, 1 over square root of n. To visualize that better, we have this graph here where again each point is a sample, in this case a sample proportion, using this number of measurements, and we again see that the spread in the sample proportions as n increases exactly scales as the population proportion plus our formula for the standard error, which is the population proportion times 1 minus the population proportion divided by n, square root of that. Okay, so what have we learned? We have defined the standard error, which is a measure of how well an estimator obtained from random samples approximates the population parameter of interest. We have derived the standard error of the sample mean and the sample proportion, and we have shown that those standard errors actually decrease with the number of measurements, so that basically, what does that show? It shows that random sampling works, right? Because if we have enough measurements, we're going to have a very tiny error of the population parameter of interest in the case of the sample mean and the sample proportion. And that's all I have. Thank you very much.